This week we've been learning about the Henderson-Hasselbach equation and how it is an effective tool in predicting quantitatively a titration of a weak acid by a strong base or a strong base by a weak acid. In a previous video, I gave an example of titrating acetic acid with sodium hydroxide. I'm going to give another example here. It's worked out. So, real quick, once again, when a weak acid is being titrated by a strong base, we are basically raising the pH up until eventually we reach a point that is known as equilibrium. And from that point onward, we no longer have a net acid, we have a net base. But what is also happening is there is a certain range in the titration where we produce a buffer. And that will be made up of the acid and the conjugate that acts as a base. In this case, acetic acid, as it's being titrated by sodium hydroxide, is losing the hydrogen off its carboxyl group and joining with the hydroxide to form water. That's the neutralization. But also, the sodium is replacing that hydrogen. We now have a salt form, which is sodium acetate. These two substances form a buffering system, and what they do is they actually slow down the progressive neutralization or acidification of the solution that they're in by either absorbing acids on this side or absorbing bases on this side. Buffers, as we've talked about earlier, are an essential part of chemical systems, both biological and industrial. Your body is made up of plenty of buffering systems to regulate pHs of various organ systems. We're using buffers throughout in industrial chemistry. It's found in food science to help keep foods preserved all over the place. So let's take a look at how we can quantify not only where we are in the titration of an acid by a strong base, but also what kind of buffer we're producing and its effective range. So first, here's our starting conditions, our initial under our ice chart. We have 25 milliliters of a 0.2 molar acetic acid solution. And we will titrate it with 35 milliliters of 0.1 molar sodium hydroxide solution. So initially, we have produced no water and no conjugate sodium acetate. So an initial, we're about to add in our base. So the way that Henderson-Hasselbach works is that we actually put in moles rather than molarity in our ice chart to find our equilibrium conditions. So to work through a Henderson-Hasselbach problem like this, we go through three basic steps. First of all, we need to find the number of moles of the reactants. We've been given molarities and volumes. We just simply multiply molarity times the volume. Of course, it has to be in liters, of course, so we convert milliliters to liters. And we find our moles, and we put them in our initial. At this point, once again, we've neither produced any extra water or the sodium acetate. We assume because sodium hydroxide is a strong base, that it will, all of this will combine with our excess acetic acid. Because acetic acid is in excess, at least at this point in the titration, we will have no sodium hydroxide left. And the amount that was lost will also reflect in the amount of our acid that was lost, giving us a remaining 1.5 times 10 to the negative 3 moles or 1.5 millimoles. Conversely, the amount of base that has been lost and thus also the acid loss, that's the amount of our other side of the acetate buffering system, our sodium acetate has been produced. So here we are in equilibrium. So from here we can take the Henderson-Hasselbach equation and figure out what is the pH now that we know equilibrium endpoint conditions of this titration. So this entire equation is made up of logarithmic transformations. pH, of course, is logarithmic. The loading is like power of the hydrogen concentration. pKa is the logarithm, negative log, of our Ka of acetic acid, which, as the books will tell you, is about 1.8 times 10 to the negative fifth power. So when we take the negative log of that, we have a pKa of 4.75. So the pH, when you're using Henderson Hasselbach, will be 4.75 plus the logarithm of the endpoint concentrations of our base over the acid. So in other words, 1.5 times 10 to the negative, 3.5 times 10 to the negative 3 over 1.5 e to the negative 3. The log of that is 0.368. We add to the pKa, and that is our predicted pH. So this gives us a snapshot of where we predict that the pH would be if we were titrating to this volume of our titrating strong base. But a couple of other things that I want to throw in there. On the pKa, just calculating the pKa alone is an excellent tool for understanding the effective buffering range of this system. Generally, most chemists will consider the buffering range of a buffer to be within 1 log plus or minus of the pKa. So if our pKa is 4.75, we treat it as a pH. And so the buffering capacity of this system to resist excess acid or excess base will be between 1 log less than that, pH 3.75, and 1 log more than that, pH 5.75. So if I prepared this buffer and I wanted to add it into whatever chemical system that we were wanting to help buffer, we would know that this is the effective range of pH that the acetate buffering system can help keep stable. So in a sense, this is a homeostasis range for a chemical system. As long as we're sort of keeping in this range of pH, we have a certain degree of stability if some more acid or base change in the system occurs. Now, of course, this isn't infinite. Eventually, if we add too much base, we will swing past this and we no longer have any buffering capacity because the acetic acid has been consumed and the pH will start going up dramatically. Conversely, if we go below, add enough acid to hit below this pH, that means that our conjugate base has been consumed, and adding any more acid at that point will start dramatically shifting the pH downward. This explains that general pattern of the titration curve of a weak acid by a strong base. If we start right about here with our initial concentration of our acid, let's say that we had about pH 2.8, 2.9, which is probably about what this acid would be here. Once we hit to about 4.75, this winds up kind of representing our effective buffering range. But once we get past the outer goalpost in this direction, the pH just swings up intensely. Then, if we go on this side, below the lower goalpost of the pH range and add more acid, the pH will precipitously